Sounds good.
Um, um, Good morning. Good morning, everyone. There are more people joining as we talk, but we'll kick things off here. And it's a real pleasure to introduce Dr. Carlos Fernandez. And Carlos is a chief scientist and team lead at Pacific Northwest National Laboratory, and he's got over 20 years of experience in industrial and governmental R&D. Before joining PNNL, he worked as a researcher and consultant for the industry sector in the Center of Excellence for Products and Processes of Cordoba, Argentina. And he joined PNNL in 2006, and since then he's focused on engineering nanomaterials, cement, and concrete composites, smart fluids for environmental and energy applications, etc. And he's led several large multi-institutional projects with a value of something like $15 million over the past 5 years. Now he's received a lot of a lot of plaudits. As of 2024, he has over 70 publications, 8 patent applications, 6 have been awarded. That's amazing. He's on the editorial board for Nature's Scientific Reports. And this is the part that impresses me, that his research has been featured in several press releases, including Energy.gov, CNE News, Chemistry World, Scientific American, NBC right now, and he's been on 10 journal covers. This is really an amazing story. And so Dr. Fernandez's work on StimuFrac, which we'll hear about today, has been recognized as game-changing technology on CNE News. And Carlos has received the 2020 R&D 100 award and a silver medal for green technology. Wow, we're so lucky to have Carlos Fernandez speaking to us today. Carlos.
Thank you, Sean. Thank you very much for the introduction, and I'm humbled to be in this seminar. Thank you for the organizing this, and as well for everybody to be joining and trying to learn a little bit from me, as well as I think I'm going to learn more from your questions that you guys from this presentation. So yeah, Sean is correct. This is a technology that we have been developing for the last 11 years now. Started as a crazy idea about using an expanding fluid to generate work create fractures more efficiently. And here we are showing the latest results. The work obviously it's teamwork. I'm just presenting what other people have been doing on my team, including Joaquin Xian, Alain Bonneville, Chef Burgard, Chef Garrison, Mark White, who recently retired, and so on, Trenton Cladojos, Lianxi from Los Alamos. So it's a great team, and the work has always been funded by the Geothermal Technology Office. So we are very grateful for that as well. So the goal of this presentation is show you what StimuFrac is all about, and at the same time give you some high-level learnings that we had in the last 10 years, and kind of discuss with the panel or with you guys what would be next on this technology. So I think probably some of you are familiar with the technology, but for those that are not, this is a very simple schematics of a polyalenamine solution. This is what we call StimuFrac. It's a polyalenamine solution. And for those that are not chemists, this is an amine, and this functionality repeats through the polymer about 200 times for each of the polymer strands. And each of those amines, since are a Lewis base, can react with the Lewis acid like CO2, CS2, or any other acid gas or acid liquid or supercritical, cross-link, form a cross-linking fluid. And this fluid expands in volume and also increases viscosity. The beauty of this is not only that, but also that the reaction is reversible. You can depressurize with the CO2 pressure added, and you get back to a solution of the polymer which you can recover with the produced waters, as well as the CO2 also recover and repressurizing in the next wellbore. So reversible volume expansion, reversible viscosity increase, and we will talk about how each of them may help aid to the efficient fracturing of rock at geothermal conditions. The polymer is highly thermally stable. We have been able to get it up to 400 Celsius, limited by the operations of the vessels. But 400 Celsius, we have the chemistry going and reversibility of the reaction between CO2 and the polymer. It's a non-toxic polymer. That's why we call it green. And also it's about 80 cents a kilogram. So it's fairly cheap. We use 1% of this polymer in water. That's everything about the solution. It's very simple fracturing fluid. So this is a speciation is basically what is the fate of CO2 and the polymer when they are both together at high pressure and temperature. And what we see here is a high pressure and high temperature magic angle spinning NMR. This is a small reactor where you can have the solution there. It's spinning at high frequencies, and then you add the CO2, and what you can see is what's going on with the chemistry, where you form an ammonium carbamate, so a protonated amine of the polymer, react with the CO2 that is already linked to a second amine, and then it cross-links, forming a reversible ammonium carbamate. That's the reason for the reversibility of the process on the volume expansion and the viscosity increase. If in some cases you have some dehydration process, you form an actual non-reversible link, which is a urea linkage. This is a typical urea bond that you see in urine, for example. But most of the reaction takes place around the ammonium carbamate, and then when the pressurizing or reducing the temperature, you go back to the amine and the CO2 free. So initially what we thought is that, well, we can use this polymer solution in the presence of CO2 that expands in volume as a way to increase stress in a confined environment. Later, you will see that this is highly dependent on temperature, and viscosity also plays a role. And another property that the fluid has is, since this is a polymer solution, it's a surfactant like soap in water, is the reduction in surface tension. So that reduction in surface tension together with the CO2, which is a negligible zero surface tension, it can make good things in terms of penetration in the wellbore. So the volume expansion is proportional to temperature and pressure. So more CO2 in it, higher volume expansion, higher changes in viscosity, all reversible in nature. Higher temperatures, the same thing. We see volume expansions that are about twice the original volume at temperatures as high as 300 Celsius. Temperatures below 300, about 200 Celsius, you still see volume expansion, but in the case of 300 and up, the volume expansion is truly visible. I will try to play this video. It's a very old video, but still it works. So the solution of polymer, and then it was, as you inject CO2 at 300 Celsius, the solution is at 300 Celsius, you can see the change in volume and formation of what we see as a single phase. So this is probably one of the unique properties of this fluid, where you see CO2 becoming a single phase with the aqueous solution. Usually you have supercritical CO2 on one phase. You may have some dissolution of the CO2 into the water, but the dissolution here is fairly large to the point that you see a single phase in the cell associated to the volume expansion of the triggered by the reaction of CO2 with the polymer and the dissolution process and of CO2 expanding that fluid. So just what you see here is not magic balls, but actually it's a window of the cell, as you probably saw here. This is the camera. You have the window here, another window here, obviously another one here, but we see a transmission video like the one that you see here. And then if you take a shot, like multiple shots in the video, you can see what you see here. So this is the meniscus. This is the cell filled with about half, and slightly less than half the fluid, the volume of the cell with the fluid, the polymer solution. And then at ambient temperatures, it doesn't matter how high the pressure of CO2, you will not see CO2, basically the volume expansion of the fluid. But as you go higher in temperature, you start seeing that pressures of CO2 as low as 11 megapascal, this is about 1600 psi, you start seeing some changes in the volume. So you still have basically the coexistence of a supercritical CO2 phase, but the volume of the polymer is expanded by the reaction and the CO2 basically getting into the solution. This expansion is like I say, it's an exothermic reaction, so temperature triggers higher and higher volume expansion and higher changes in viscosity. And what we see, for example, at 400 Celsius, this is, for example, if you want to go super hot HES at 400, 450, 475, or 500 Celsius, I believe we can get expansions at as low as 1600 psi and changes obviously on viscosity. So this fluid expands at lower pressure of CO2 as you have higher temperatures in the cell. We did control experiments, numerous of those, and just same amount of water, but no 1% polymer here. And it doesn't matter how much you pressurize with CO2, you will have always two phases and no expansion of the aqueous solution. Since the reaction is reversible, like I showed you by NMR, nuclear magnetic resonance, you can see that the volume expansion takes place at 300 atmosphere. This is 4,500 psi at 300 Celsius, and then you depressurize and you get back the polymer solution. Then expands again with more with repressurizing with CO2, and then you get a polymer solution. We did this several times. You get slightly less expansion, but because I think what happened is you have a little bit of irreversible reaction going on, but other than that, most of the reaction takes place via a reversible interaction between CO2 and the polymer. The viscosity, so we compare the viscosity, and unfortunately the rheometer can go up to 190 Celsius. So we see some changes in viscosity, not as high as I would expect at higher temperatures, but nevertheless, this is time, this is viscosity values, and this is pressure. As you start increasing the pressure of CO2 at 190 Celsius, so you have a little bit of vapor pressure from the water, and then as you start increasing the pressure of CO2, sorry, this is the pressure of CO2 here, about 120 atmospheres, which is about 1600, 1700 psi, you will see that the polymer solution start reacting with CO2 and increases viscosity. We then depressurize and the viscosity goes down to near water. And then we can do this over and over again and get viscosity increases. The viscosity is about 15 centipoise. It's not huge, but again, the temperature and pressure limited by the rheometer are in the lower limit of changes in rheology of the polymer solution. If you have a sodium dodecyl sulfonate, which is a typical surfactant used in oil and gas, as well as xanthan, there are changes in viscosity, but not as high as in the case of a polymer solution at these temperatures. The fluid also shows shear thinning behavior, so it can be injected or co-injected with CO2 at high shear rates, and the viscosity will be similar to water. So you can pump this as you pump water, and then as the shear rate starts decreasing, and let's say the polymer solution with the CO2 or the polymer solution alone start getting into the porous network of the rock, the flow rate will start reducing, and you can see that the viscosities are about an order of magnitude higher, to 2 orders of magnitude higher than water, just because of the reaction. Again, this process of viscosity change increase and is reversible with pressure. So we say, okay, how we can use these rheological changes with CO2 to fracture rock, and how this compares to other fluids like water, which everybody's using, and a waterless fluid like CO2, a combination of the water plus CO2, similar to a combination of StimuFrac which we call the polymer solution, interchangeable, and CO2. So the best control would be water versus with CO2, right? Because it's the same experiment, the same volumes, the same everything, but in the absence of polymer, and then obviously StimuFrac CO2. So what we did is we have a very simple flow reactor, and it was made in 2014. And inside the flow reactor, we have a rock sample, and this rock sample is inside a I would call it a cradle. The rock sample has a wellbore that is blind, and then that wellbore is about 200 microliters. And then this wellbore is isolated by a graphitic O-ring from the confining pressure outside the sample. These groups around the sample, actually what it does is allows the confining pressure to be fairly homogeneous distributed around the rock sample. So the experiment is very simple. We have water as a confining fluid. It's an isotropic pressure. Obviously, it's not what we see down the subsurface, but at least for the experiments to have multiple rocks surrogates to evaluate the different fluids, including StimuFrac CO2. This was a good start, and so the condition is 3,000 psi of fluid exerting on the rock, and then 200 Celsius. All these experiments were limited by temperature pressure, because the pressures that we got this flow reactor to were close to 8,000 psi in some cases, depending on the material, but depending on the rock. But what we're seeing with this is the operating temperature limit is 200 Celsius, and the operating pressure, because the operating pressure is close to 8,000 psi. So 200 Celsius, as you remember, is not a large volume expansion, but we see some, and also some change in viscosity. So what we did here is we pressurize the rock, and then we pressurize with either water or CO2 if we are trying single phase fluids, or water followed by CO2, or polymer solution, the StimuFrac followed by CO2. And then we increase this at constant flow rate until the pressure inside the wellbore, which is this taken by this gauge, pressure gauge, equilibrates with the pressure around this wellbore. That means you have a fracture connected. These are diorite samples or Newberry samples. We did multiple of those. And when you fracture, basically you have a connection between the wellbore and the walls of the sample. This sample is about close to 1 inch in diameter by 2 inches in length, very small samples. So what we see is consistently, particularly with StimuFrac CO2, very high increases in permeability or fracture, permeability in this case, of the fractures generated by StimuFrac CO2 at 150 Celsius and 3,500 psi. We always generate this kind of planar, parallel to the wellbore direction fractures. And what we've observed was not only that the fluid was fracturing, the StimuFrac CO2 was fracturing at lower pressures than conventional fluids like water, CO2, or the combination of water and CO2, but also that the permeability of the material of the sample was significantly higher, orders of magnitude higher than in the case of the same sample in the absence of the polymer, so water, CO2. And this was not only at lower temperatures of 150 Celsius, but also at temperatures as high as 300 Celsius. We were able to run some, push the limit of the reactor to 300 Celsius and get similar results where we have very high permeability using StimuFrac CO2 versus the same solution in the absence of the polymer. And then what we did is basically ran a single core. We got multiple samples, about 9 samples out of this a single core of Kosovo at 200 Celsius. And we repeat experiments, 5 experiments with water CO2. So basically the same experiment in the absence of the polymer, and then with polymer solution CO2. And what we observed was 2 things. One, the variability of the effective pressure or the breakdown pressure was very high for PAA CO2, while for water CO2 was fairly constant. And also that the average effective pressure to fracture this rock was lower, at least even though the variability was high compared to the water CO2. So we say, is the volume expansion actually doing some stress local that when we measure the pressure, the pump right here, we see a lower pressure when we fracture with polymer solution CO2 than with all the other fluids, including water CO2. Is the localized pressure that doesn't communicate to the pump? We should fracture the rock at the same pressure independently of the fluid, but it doesn't seem to be the case. So what could be that? So what we did is, well, rocks obviously are heterogeneous in nature, so we have to find something that is more homogeneous, and we use quartz, or actually fused silica. This is a non-porous material, and we prepared samples. We bought the sample from a third party, but with the same geometry and wellbore geometry as well. And we wanted to surrogate that it's very homogeneous. We know by simulations at what pressure will fracture 24 megapascals. And we did several fluids, including water, about at least by triplicate. We fractured this, always fracture in a 45 to 40 to 50 degrees angle. And we thought that maybe the pH, CO2 is an acid gas, so it may reduce the pH. As this is not associated, this decreasing breakdown pressure by polymer solution CO2 is probably pH thing. No, it's not, because we add hydrochloric acid and we fracture, and we are getting similar values within the variability of samples to the breakdown pressure at which quartz or fused silica should break. The same for CO2. When we go to water CO2, we have more variability than the other 3, and also slightly lower pressures, about 5 megapascal, 3 megapascal lower. But when we use a polymer solution CO2, the pressures at which we fracture are even lower. So similar to what we see with the Kosovo samples, but now in a very homogeneous surrogate material like fused quartz. So, and this is, pardon for all this is just copy and paste for the paper, but what we thought is maybe there's a shell that is being formed. We fill I forgot to say that the polymer solution of the water solution, the water without the polymer, we add 200 microliters. So we add around similar volume that the wellbore volume. And then we start adding, we swap the pumps, and we add, so we added through a T. So basically there is no PAA or polymer solution of water outside the wellbore. And then we add CO2, and we start at constant flow rate, increasing the pressure. And what we think will happen is that the polymer solution, in the case when you have polymer, the CO2 will react with the polymer solution and form kind of like a shell or some sort of a material that will have very low compressibility, but at the same time, since it's expanding in volume, it may have, and it needs to have, 2 things to be able to have a localized pressure that it does not communicate to the pump. One is high shear strength, so the plug doesn't, just get expelled from the wellbore. And second, a very high bulk modulus. And in that way, and that only way, a radial direction stress will be generated locally and then those pressures that we measure at the pump that are lower than all the other fluids is because the rest of the pressure to get to the values at which we fracture the rock or the fused silica is added by this localized pressure associated to the shell expanding in volume. Well, the response to that is no. We measure the viscosity, obviously not here, but in the rheometer, and yeah, independently of the volumes of fluids, which may affect the viscosity, and the experimental conditions, which is not in the wellbore, but actually in a large vessel of 20 milliliters. But nevertheless, we measure that the bulk modulus is only 650 Pascal. And assuming a volume expansion of 35%, which is what we see at 200 Celsius, look at the pressure, negligible. So this rules out that there is expanding shell. There are some limitations to rheological properties that we measure the viscosity, but nevertheless, we cannot justify that reduction in pressure associated to the volume expansion of the fluid. So we went to a next experiment because we wanted to measure the volume expansion, the stress associated to the volume expansion in a larger vessel. So this is I think it's a 40 milliliter vessel. It's a flow reactor. It's a very simple reactor, but it has a key component. It has inside a piston that separates two volumes. We can inject polymer solution or water on one side, and we can inject CO2 on the other side. They will not mix, so this is a constant volume cell. They will not mix unless I move the piston. When I move the piston, there are 4 plugs, unfortunately I don't have the pictures, but 4 plugs of Teflon that will drop. They will just drop if we mix it, if we move the piston in one direction. And we have a bar here that move the piston, is not showing here. But those 4 plugs will drop, and then the piston is obviously permeable because the plugs are gone, and the CO2 and PA will mix. The goal of this is to avoid any dead volume or any change in constant volume. So with this experiment is a constant volume, and see if this reaction at any given temperature and pressure generates a volume expansion. It does generate work, stress, okay? We did this at 200 Celsius, again, limited by the operation temperature of the reactor. But what we see is the following, and this is very important. We do see an overpressure relative to the water CO2 because we did water CO2 3 times and polymer solution CO2 3 times, 3 experiments each time. So hence the error bars. And what we observe is when we do water and we open the valve at 6 megapascal of CO2, we get around 1 milliliter of CO2 in, and then we close the valve of this reactor. We close the valve of the reactor here. This is already closed. We have a constant volume with constant mass of CO2 added, about at 6 megapascal, about 1 milliliter, and polymer solution. So most of the cell is filled with polymer, and then we add a milliliter of CO2. So at 6 megapascal, we close the valve, and what we see is that in the case of water, the 6 megapascal goes down to 2 megapascal. And this is understandable because when you add CO2 in water at these pressures, we have a dissolution process that will generate a pressure drop, okay? When in the case of polymer solution with CO2, we add at 6 megapascal, well, we close the valve, we let it react, and stays at 6 megapascals, 6.5 megapascals, okay? So what happened here? Yeah, there may be a volume expansion, it's about 30%, at 200 Celsius. But the volume expansion compensates for any pressure drop associated to the dissolution. There is enough volume expansion that associated that does additional work to 6 megapascal of the original pressure at which CO2 was added. So yes, there is an overpressure relative to water CO2, but there is no work in that cell associated to the expansion. It's just compensation for the pressure drop associated to dissolution of CO2. Then we open that valve and we continuously added more CO2. And what we see is an increase in pressure, obviously, in the water solution as well as in the PA solution. Yes, the volume expansion aids to higher changes in pressure for the same volume of CO2 as in the case of water. So yeah, the volume expansion does increase the pressure higher at any volume of CO2 than in the absence of the polymer. But what we believe is there is no, at this temperature, okay, 200 Celsius, there is no work associated to the volume expansion. So at 200 Celsius, we cannot say that the fractures were generated at lower pressure because there is a volume expansion and a localized pressure in that wellbore, that small wellbore that we showed previously. So this is just a comparative of the technology versus what we compare with water CO2. You add CO2 in water at constant volume, you will have a pressure reduction because of the dissolution of CO2 in water, partial dissolution of CO2 in water, so you have a pressure drop. With PA CO2, the polymer solution CO2, again, I always say 200 Celsius. I would love to have an instrument that I can measure at 300 and 400 Celsius, but at 200 Celsius, at constant volume, there's compensation for pressure drop for dissolution, but there is no additional pressure associated to the volume expansion at 200 Celsius. Propellants, just to give you an idea, propellants will obviously expand. This is a gas reaction much faster than a StimuFrac CO2 reaction. This takes in 10 to 30 seconds versus milliseconds or microseconds in case of propellants. And you will have obviously a pressure or work associated to the actual expansion of these gases. So this is just for you to know that 200 Celsius, the work associated with the polymer solution with CO2, additional stress is not observable. So another, I don't know how we're doing with time, 38 minutes. Okay, so I will go faster. Another property is interfacial tension. So the interfacial tension between StimuFrac and a porous material and as compared to water was measured indirectly by flow rate, measuring the flow rate, and what we observe in a packed silica flower bed. This is very fine sand. We observe that the flow rate's about 19 times higher than water. So StimuFrac does reduce the interfacial tension because the viscosity is similar, the interfacial tension of water, and that could play a role in because lower interfacial tension in Penn State paper shows that means lower critical invasion pressure. And if you have a lower critical invasion pressure in supercritical fluids, you will have you will generate fractures at lower net pressures. So bottom line, at 200 Celsius, again, I always remind this to the listeners. Yes, there is a small volume expansion, about 35%, but there is no overpressure associated to the volume expansion. We couldn't measure it. Yes, the lower interfacial tension may aid to the reduction in pressure, breakdown pressure of the rock or the surrogate silica. But how about viscosity? There is a viscosity increase associated to the reaction, right? So for that, we go to the one, we would move from inch scale to half a foot scale. We built this reactor. Chef Burgard was leading this, a great colleague of mine, and he basically designed this foot scale system through triaxial frame where we have a granitic rock, half a foot in size, cubic, and then a wellbore with two puckers and a concentric wellbore. So where you can inject CO2 and polymer solution through different tubes, concentric tubes, and they will meet here. And then you have a notch that will guide the fracture because the minimum stress was purposely on the vertical direction. And then this notch will guide fractures. These are granitic materials that are not, that they don't have natural fractures. They are just porous, about 2 to 3% porous materials, but the lowest minimum pressure stress in the vertical direction, and with a notch, what you guarantee is that the fracture will generate horizontally, and always it will be reproducible from sample to sample. So the confining pressures, these are flat shocks that we use on these two directions. And then the vertical load is a frame that we put a vertical load, 1100 PSI versus 1400 and 1400, 200 Celsius. Again, this is an open rock. And we tested, again, all the fluids, just water, as everybody's fracturing with water so far. CO2, no water presence. And then introducing water to the rock, about 1/3 of the pore volume of the rock. And then followed by constant flow rate of CO2. And the same exact experiment, but with polymer solution instead of water, 1% of the polymer, polyamine, followed by CO2 injection at constant flow rate. And we did these experiments in the lab, and what we envision in the field, so this is in the lab, we basically add this polymer solution at constant pressure, 1000 PSI, and we let it impregnate slowly into the transport into the rock. And then about 1/3 of the total pore volume. And then once we have that, we add a constant flow rate CO2 until we fracture, okay? In the field, what we envision is doing a polymer alternating CO2, where we add fresh polymer, fresh CO2 in multiple cycles to propagate the fracture and continue the reaction at the tip of the fracture towards fracturing away from the wellbore. But this is a single cycle polymer or water followed by CO2 is what we did in the lab. But obviously, first, just water in hot, dry rock. So the rock is at 200 Celsius. We start fracturing. We start constant flow rate of water until we fracture. We observe that with water, even at very high flow rate, we went all the way to 25 milliliters per minute, and you will see it in later slides. The pressure drops are fairly large compared to a lower flow rates, but the hydraulic conductivity in cubic micrometers was very, very small, independent of the flow rate. Hot, dry rock, so we don't add previously water to saturate the sample. When we add CO2, just CO2 without any water in the, except for whatever water is remaining at 200 Celsius in the rock, so hot, nearly dry rock. Again, we need high flow rates to be able to see these large pressure drops and decent hydraulic conductivities or fracture conductivities, okay, across the entire, this is the notch of the sample, and it goes all the way to the wall of the cube, of the half-foot scale cube. Higher flow rates are the only way that we can get with CO2 alone decent hydraulic conductivities for that scale. For water, so putting 1/3 of the total pore volume and followed by CO2 at constant flow rate. So first we impregnate with water about 1/3. The total pore volume was 33 milliliters or 30 milliliters actually. And we add about 10 milliliters of water at constant pressure below the minimum pressure stress. And then we swap the pump to CO2 and we inject CO2 until we fracture. Again, with water CO2, low flow rates of CO2 will not generate any fractures. But high flow rates, you get these pressure drops and these decent fractures, similar to CO2 alone without adding water. But this is a control, the perfect control for polymer solution, CO2, where we add now the polymer in that water. Again, 1/3 of the total pore volume. And what we see is large pressure drops independently of the flow rate. 2 milliliters per minute, 10 milliliters per minute. We consistently get very high pressure drops and significantly higher permeabilities than the other fluids, particularly water, about 2 orders of magnitude higher hydraulic conductivity, sorry, than water. And you can see the fractures propagate. They kind of self-prop across the entire, from the notch area in the center of the wellbore all the way to the fracture, to the walls of the rock. These are thin sections, by the way. So we wanted to know what happened when we saturate the rock with water. So we have the rock at constant pressure, 1000 psi, with water for one entire day, 24 hours at 200 Celsius. And what we see is that the permeability of water increases as more water is getting into this formation rock and in the rock sample. And after that, we performed exactly the same experiments with CO2 in the presence and in the absence of the polymer. We narrowed to the two systems, water followed by CO2 and polymer solution followed by CO2. And what we see is the following. In 1 day water saturated rock, we need to pump at 25 milliliters per minute. So we pump 1/3 of the total pore volume after water saturation for 1 day. At 1000 psi, we continue adding 1/3, about 11 milliliters more of water before we inject CO2 at constant flow rate, 25 milliliters per minute, limited by the pump flow rate. And we get a sudden pressure drop, fracture that communicates, but these are more or less the hydraulic conductivity or the fracture conductivity of when you use CO2 in the absence of the polymer. In the presence of the polymer, so in the same 1 day water saturation, and then you add 10 to 11 milliliters of polymer, followed by constant flow rate of CO2, you get very large pressure drops, higher than in the case of water, and about an order of magnitude higher consistently, because these are least triplicate samples, consistently higher hydraulic conductivities of fractures. And you can see the fracture much better in this thin section as compared to the case of the absence of the polymer with CO2. And we did 3 days as well, with 72 hours, just pumping water, trying to saturate the rock as much as we can in situ. And then we follow by adding, just fracturing with water alone, no CO2, just swap to constant flow rate and fracture. These are the hydraulic conductivities. The same thing, but after water, we add CO2. Again, some pressure drop. These are the conductivity is very low for 3 days. And the polymer solution, StimuFrac CO2, higher pressure drops, but still bigger, larger than water CO2 or water alone, but much lower than before. So it looks like the water saturation of the rock, and this is a paper that we just published, plays a key role in the performance of any fluid in terms of efficiency in fracturing and increasing permeability. So what we think is we may be able to use, because maybe dilution issues we're having here, we may be able to use a higher concentration of polymer solution to be able to fracture more with much higher hydraulic conductivities. But for now, when you have 3 days, the water saturated rock, you have these results. And what we observe also is that the breakdown pressure that in small samples, 1-inch samples for StimuFrac CO2, polymer CO2 were lower than any other fluid. Now they are higher at 2 milliliters per minute, fairly similar at 10 milliliters per minute in hot, dry rock. And in water saturated rock, yeah, higher than water and CO2 at 25 milliliters in 1 day saturation and 3 day saturation. So again, the breakdown pressure here didn't show us a low value as compared to other fluids like in the inch scale samples. And again, at 200 Celsius, we don't think that the overpressure is associated to there is no overpressure associated to a volume expansion. Having said that, the fracture conductivity enhancement is significantly higher for StimuFrac CO2 than any other fluid. So about 1 to 2 orders of magnitude higher when we fracture at low flow rates in hot, dry rock. When we fracture at higher flow rates, it's statistically similar, but we have an outlier here with CO2 where we have very high permeability, fracture conductivity for one single sample out of the 5. But nevertheless, it was similar in statistically similar, but higher than water or water followed by CO2. And then in water saturated rock 1 day and 3 days, we get, again, higher hydraulic conductivities than the other fluids. So yes, there is not a breakdown pressure difference is actually sometimes higher than the other fluids, but we have significant larger hydraulic conductivity of the fractures independently of the flow rate and independently of the water saturation of the rock with StimuFrac CO2. We did some simulations, and I will go, so I want to leave room for questions, stump simulations. And what we observe is that in the fluid that has higher viscosity, we have, this is the pressure as a function of distance from the wellbore. We have, this is a minimum principal stress in the vertical direction. In the case of water, in the case of CO2, in the case of water followed by injection of CO2, we see a pressure envelope that is below the minimum principal stress except close to the wellbore. In the case of polymer solution, particularly when it reacts with CO2, the viscosity is increased, so you have a larger pressure envelope away from the wellbore at pressures above the minimum principal stress. We believe that that, in combination with the lower interfacial tension of StimuFrac, are the main mechanisms associated to a more efficient fracture and fracture conductivity post-stimulation, and not due to the overpressure. So what we think is that this high stimulation efficiency for StimuFrac CO2 is a combination, and this is just a hypothesis, a combination of low interfacial tension, which has a low critical pressure, invasion pressure. So you can penetrate polymer solution much farther away from the wellbore because of the low interfacial tension. And then when you inject CO2 and start reacting, you build viscosity to the point where you have very reduction in leak off and concentration of pressure above the minimum principal stress away from the wellbore, fracturing in that way more efficiently, to the point that we see self-prop fractures. Bottom line, the mechanism we believe is at 200 Celsius, again, overpressure has negligible to none impact on the efficiency of the fracturing with StimuFrac CO2, but a combination lower critical invasion pressure due to the lower interfacial tension, together with the higher viscosity increase, reversible viscosity increase, is what causes this very high self-prop fractures. And I will leave this take-home message for you guys. I can share the slides, but what we observe in bottom line, I want you to remember is two things. One, the StimuFrac outperforms all other fluids in terms of permeability enhancement, about 2 orders of magnitude higher hydraulic conductivity of the fractures post-stimulation compared to water, independently of flow rates, independently of water saturation. StimuFrac volume expansion does not play a role, but this is at 200 Celsius. Remember that the volume expansion starts being at least twice the original at temperatures above 300 Celsius. So that's why we would like to do this in the field at temperatures above 300, super hot HES also. A combination lower interfacial tension and viscosity increase is what we believe is the reason why we get more efficient self-prop fractures, tensile fractures. And finally, water saturation plays a very important role in fracturing fluid performance. This is new for us, I don't know, for you guys. We published a paper where we saturate the rock for different amount of times, days, and we see that the fracturing fluid efficiency drops independently of the fluid because of the saturation of water. We don't know exactly what's going on, but that's the case. So we have done age scale, foot scale, and we are ready for field scale. Try to learn from what we observe in terms of conditions at which we fracture more efficiently at the field. With that, thank you very much for your attention. And well, I'm open to, sorry for the amount of time, but I'm open to any questions if there is any time left.
Oh, there is time, Carlos, and thanks. That was the outstanding presentation, really fascinating. And let's just go to the chat and see the questions. And so the first question is from Ed Siebritz, and Ed would like you to elaborate a little bit more on the field applications that you have in mind. He indicates that when injecting a frac stage down hole, the temperature of the injected fluid is cool, although near the crack tip, the fluid is warmer due to some reservoir heating. And he'd just like you to say a little bit more about what you would have in mind in the field.
Very good question. So we either will need to or preheat the fluid, the polymer solution, or enable the polymer solution to get to temperatures above 150 Celsius. We see viscosity changes at temperatures above 150 Celsius. Interfacial tension, independently of the temperature, we believe it will be very low, sorry. So we will have seepage and transport the fluid into the well through the porous. You will think that granitic rock is non-porous or is very low permeability. You're actually wrong. The actual cubic sample that we see here, if you leave the sample at 1,000 psi of CO2 below the minimum precise stress that we apply, the waters just continue getting in. So what we will do here is inject a given volume of polymer solution first, let it seepage and transport into the formation rock, let it get to a temperature at which we believe the reaction will have some, if not volume expansions, a change in the viscosity to the point where you can add then constant flow rate of CO2 and generate these very large pressure envelopes away from the wellbore to fracture. That's how we see it. That's the stimulation plan that we have. And then obviously we will cycle, that's what we call polymer alternating gas, or PAG, cycle fresh polymer solution, fresh CO2 to continue that reaction away from the wellbore.
Great. And Luke Frash, Luke was asking if they have been tried in the field. I think the indication is you're looking for opportunities.
That is correct, Luke. We haven't had one yet. We actually did. CTO was kind enough to give us an opportunity through the Wells of Opportunity project. And unfortunately, well, Zach is here. We have issues with CIRC is a company, not because of their not willingness to help, but budgeting and so on. So we haven't been able to get to the field yet. The idea is we already have a stimulation plan on paper. The idea is just to get an opportunity where we can deploy this. If we can deploy this at temperatures above 200 Celsius, even better. We would like to see this in super hot ECS as well. But for now, everything is lab work.
Okay. Now, and Luke has he's a couple of others, but I think you've answered those. And then he has another question. Can you elaborate on how you measure fracture conductivity in?
Oh, great point. Yes. And I didn't touch on that because of time. So let me show So let's say I want to show the actual system. Okay, so first, this is a concentric tubing. We performed the fracturing, the stimulation test. We did more than 40 tests. This is huge endeavor, about 3 years of work, because we wanted at least triplicates. Once we fracture, we generate the fracture and we see the communication because there is a large pressure drop, particularly with the StimuFrac CO2. We follow that at the same, still apply the confining pressure with flat shocks and the load, the frame load. We add an oil, a silicone oil fluid to measure the conductivity under those same confining pressure at which we fracture. So the hydraulic conductivity is measured by constant flow rate at different small and constant flow rates to get the values that I can send you the paper if you want, but that we use the same fluid at the same temperature and confining stress conditions. But in this case, silicone oil.
Okay, cool. And Arash is interested if there's a dependence on salinity for the reaction.
Salinity?
Yes.
Oh, great. Okay. Yes, actually, there is not. We have a project. So as you probably will guess, we have from the oil industry a lot of traction in earlier times, and for different reasons, we haven't been able to deploy in high temperature fossil fuel recovery. But we have a lot of interest, and we have done tests funded by an oil company where we have a highly saturated brine, and they wanted to see the viscosity changes under high concentration of brines. And what we observed is that the viscosity was very similar. Usually large brines, like highly concentrated brines, have a reduction in viscosity, make the water viscosity make it reduced. Don't remember exactly what's the reason why, but when we inject CO2, we get the viscosity similar to when we inject CO2 in tap water, and the viscosity change as long as you keep that CO2 pressure in the well, in the reactor, in the rheometer constant, the viscosity will maintain constant, and they wanted to keep that viscosity constant for several days. I think we did 48 hours, and the viscosity didn't drop in the presence of the brine. So yeah, the reaction takes place independently of the ionic strength of the fluid.
Okay, well, that's an excellent answer. We have a couple more questions, so I'll bare my soul and ask a naive question. So I'm curious about the kinetics of the polymerization. You've got a polymer, and you've got a supercritical fluid that's going to diffuse into the polymer. Does the change in the viscosity and the pressure that's developed inhibit the diffusion?
Yeah. What I can tell you, this is a question that we had since the beginning, because these are two different fluids. They are non-miscible, except that the reaction triggers that miscibility because it drives CO2 into the solution, and that's why you see this volume expansion, or at least that's what we believe the volume expansion is taking place. Now, if you have a wellbore, and then let's say you add first the polymer solution, you let it seepage into the formation, and then you displace the rest of the column of polymer solution with CO2 until the CO2 goes in. The solubility, the mixing of that of those two fluids inside a wellbore and into the formation is unknown. What we can say is that both StimuFrac and the polymer and the CO2 have very low, particularly CO2 is basically nearly zero. Supercritical CO2 is nearly zero surface tension, interfacial tension. So I would guess there is miscibility, mixing and transport of one fluid into the other one and into the formation due to the very low interfacial tension together with very low interfacial tension. But once this fluid gets to temperature and start reacting, I will say that will happen in an injection wellbore, that will happen into the formation and away from the wellbore when the temperatures are higher. You start building viscosity. You're correct. So that viscosity may reduce the mixability of the fluid, but at the same time, these fluids, due to the very low interfacial tension, they may have already mixed. So then what the viscosity increase does is reduce the leak off of CO2 into the formation, and you get these pressure envelopes that you saw in this in the storm simulations. So what we think is the combination of the low interfacial tension that enables miscibility into of the two fluids, together with the increasing viscosity to prevents leak off of CO2 is what it does generate these large fractures. But again, we haven't done, this is just a hypothesis. We haven't done the work to be able to distinguish or to measure how the CO2 is mixed into in the polymer solution in an actual wellbore. This is something that maybe there is an experiment that you can think of. Let us know. We will be happy to do.
Far out. That's very interesting. And one last question from Ed Sieberts. Ed says you mentioned the production of urea. When does this happen, and is it a precipitate or a fluid?
It's actually it's a precipitate, but what we have observed that the concentration of that product is significantly smaller than the actual concentration of the ammonium carbamate, and this was observed by NMR. So yes, this is highly dependent, obviously, on temperature and pressure. The higher the temperature and the higher the pressure of CO2, the more reversible the reaction is, the less goes toward the hydration and formation of urea linkage. So the higher the pressure and temperature, what we observe in the view cells is less and less precipitation and more of a reversible interaction.
Excellent. Well, we're out of time. I mean, really a fascinating presentation and awesome piece of work. I hope the community finds a place for you to try this out in the near future. So thanks everyone, and we'll see you in a couple of weeks.
Thank you very much, Sean. Thank you for the opportunity and great seeing you. Thank you, everybody.
Thank you, Carlos.
Bye-bye.